organisers for the opportunity to speak, and for all their hard efforts, especially over the last couple of weeks. I think they've had to do a lot of work, much more than they were probably expecting a month ago. Perhaps another thing I want to say is I find it a little bit strange that I'm here at the Newton Institute at this time, because I think the story goes, isn't it, that Newton made his big discoveries about gravitation, that he had to flee Cambridge because Cambridge was shut down because of the plague, and so he fled Cambridge, went to his country home, and it was only then that he sat down and discovered his theory of gravitation and all that. So potentially much great mathematics is going to be done over the next 4 months while we're all self-isolating. So today I want to speak about simple groups and graph symmetry. Essentially I want to talk a lot about how, say, the classification of finite simple groups has enabled us, and many people, mathematicians, to do lots of work on classifying graphs with certain amounts of symmetry. So just to set up a little bit, so we'll have gamma will be a graph. Okay, and so for me, this is always going to be finite and will always be connected. Okay, and I suppose simple. So I won't have multiple edges. For now, a graph is a graph in that it's undirected, but later on I do want to talk about directed graphs as opposed to digraphs. Now then, what do I need? So my graph, I have a collection of vertices, and I talk about vertices being adjacent. And I can also talk about arcs, okay, and this is just an ordered pair of adjacent vertices. Okay, so my graph. Simple just means that there's no multiple edges between the vertices, between pairs of vertices. And no loops. Yes, and no loops as well. Okay, so I've got vertices, I've got edges, which are my pairs of adjacent vertices. I can also talk about an ordered pair of adjacent vertices, so they're my arcs. I can also look at my automorphism group of my graph, so aut gamma. So these are all the permutations of a vertex set, which map adjacent vertices to adjacent vertices. And I will look at subgroups G of the automorphism group. Now I can then look at what sort of symmetries we have. And so the standard ones would have vertex transitivity. Okay, and so I'd call my graph vertex transitive if my automorphism group acts transitively on a set of vertices. Sometimes I would want to restrict myself to a subgroup, and I could talk about G vertex transitive, which just means that my subgroup G is transitive on a set of vertices. I can also talk about edge transitive. I could also talk about arc transitive. Okay, so this is now when I'm transitive on a set of arcs of my graph. Okay, and if I just say arc transitive, I'm meaning that the automorphism group acts transitively on the arcs. And in some cases, maybe I want to just talk about some group or subgroup of automorphisms, and I'll talk about G arc transitive. Now, another particular thing I want to focus a lot of attention on is the notion of an S arc. So S is an integer, and this is just an ordered, well, an S plus 1 tuple. I suppose that's using more words than I need. An S plus 1 tuple is always ordered, but anyway, I have an ordered S plus 1 tuple, so I have vertices V0, V1 up to Vs, such that they're pairwise adjacent, so Vi is always adjacent to Vi plus 1. Okay. And also, I'm not allowed to go automatically back on myself, so Vi is not Vi plus 2. So in my graph, okay, so something like, okay, that would be like V0, V1, V2. Okay, that would be a 2 arc. That's also a 3 arc, but equally going back around in that. Okay, I'm allowed to have some repeated vertices here, but I just can't immediately go back on myself. Okay, so a 2 arc, I can't go there for my 2 arc. Okay. So that's the notion of a S arc. And then, of course, I can also talk about S arc transitive. Okay, so I can talk about S arc transitive, and again, this is where my automorphism group will be transitive on the set of S arcs in my graph. And if I'm interested in a particular group G, for which that's the case, I'll talk about GS arc transitive. So one arc, that's just an arc. One arc transitive is just arc transitive. So let's give a couple of nice examples. Well, perhaps if I take the complete graph on n vertices, you think that's a graph with lots of symmetry. It's got the whole symmetric group as its group of automorphisms. Well, this is a 2-arc transitive, but not 3-arc transitive. And it's not 3-arc transitive just because, well, if I look at K4, right, that's my 4 vertices. They're all pairwise adjacent. Okay, I'm not 3-arc transitive because there's 2 different sorts of 3 arcs. Okay, so starting here, that's one 3-arc, but equally that's another 3-arc. I can't map the first to the second, so I'm not going to be 3-arc transitive. But I am 2-arc transitive. Okay, so let's call this example 0. Example 1, something a bit more interesting. Let's take X. This will be a 3-dimensional vector space over a finite field. Okay, so GFQ. Okay, I'm going to take delta 1. This will be the 1-dimensional subspaces. I'll take delta 2. Will be the 2-dimensional subspaces. And my graph, gamma, its vertex set, that's denoted by B gamma. This will just be delta 1 union delta 2. Okay, and adjacency, well, adjacency is just going to be inclusion. Okay, so if I have a 1-dimensional subspace and a 2-dimensional subspace, that will be adjacent in my graph if the 1-dimensional subspace is contained in the 2-dimensional subspace. Okay. So really this is just the incidence graph of a projective plane. And then if I take my group G to be the automorphism group of PSL3Q, so PSL3Q acts transitively on a set of 1-dimensional subspaces. It acts transitively on a set of 2-dimensional subspaces. There's this outer automorphism, the graph automorphism, which interchanges these 2 sets. So now I am actually transitive on the vertex set. And actually, in this case, I will be 4-arc transitive. Okay, and its valency Q plus 1. So that's just the incidence graph of a projective plane. Okay, so next, let's have another one. Let's keep with this theme. Now I'll take X, will be a 4-dimensional vector space. Still over my finite field. And now I'll be equipped with an alternating form. So a non-degenerate alternating form. Okay, so that means it's a bilinear form on my vector space. But if my form is B, B of V, V is 0 for every vector, right? So that is okay, and it's bilinear. And then what are my vertices of my graph? Well, again, I'm going to have two sets. I'll take delta 1. This will be all the one-dimensional subspaces. And delta 2, these will be the totally isotropic two subspaces. So by totally isotropic, I mean that the form vanishes on those things, right? So that is B of V, W is 0 for every pair of vectors in your subspace, whatever we're calling our subspace. Let's see. So since it's an ordinating form, all my one-dimensional subspaces are totally isotropic anyway, and then I just take the two-dimensional ones, which are also totally isotropic. And then our graph is like we did before. So we've got B gamma, which will be delta 1 union delta 2. Okay, and adjacency again is inclusion. And at this point, I will restrict Q. Okay, so for Q to be a power of 2, okay, we have G being the automorphism group of our symplectic group. Okay, this will be 5-arc transitive. And I suppose we're still valency Q plus 1. Should note. Okay, so again, PSP for Q for any Q is transitive on each of these two sets, but in the case when Q is even, you have the nice graph automorphism of PSP for Q. That gives you a duality of, this is really a generalized quadrangle. There's a duality interchanging delta 1 and delta 2, and that then gives you vertex transitivity. And it turns out you're actually in 5-arc transitive in these cases. So that's another nice example. And I wanted to finish with my examples with one more. So instead now let's take Q to be a power of 3. And I'll take my group G, will be the automorphism group of G to Q. Okay. And in this case, again, I won't write down all the details, but there's a nice, if you want to call it a, depends on what language you use, but either you say the building attached to G2 of Q, or the generalized hexagon attached to G2 of Q. You've got points and lines. When Q is a power of 3, there's a nice graph automorphism of this group, which interchanges the points and lines. So then I will get a vertex transitive graph. Okay? And in this case, I'm going to be a 7-arc transitive. Okay, and still valency Q plus 1. Okay. So really, I suppose that's projective plane, which is called a generalized triangle. Here we've got a generalized quadrangle, and here I'm getting a generalized hexagon. And the graphs I get have nice arc transitive conditions. Well, okay, so the first question we can ask is, well, how large can S be? Right, I've given you something which is 7-arc transitive. So there's a nice old classical result of Tutt, who really started all this off, which is 47 and 50, sorry, my memory, 59, right. So the two papers, and that is that if gamma has valency 3, okay, which means every vertex in my graph has exactly 3 neighbors, and if it's S-arc transitive, for some S at least 1, then? Well, there's two things we can say. The order of your vertex stabilizer is at most 48. And S is at most 5. So for a valency-free graph, we can only get S at most 5. So actually, if we go back at our examples, if I take Q to be 2 in my projective plane case, that's valency-free, and I get 4 arc transitive. And here, if I take Q to be 2, that's also valency-free, and it'll be 5 arc transitive, so that's as good as you can do. Now, Tutt's result has motivated a huge amount of work. If we think back, if we forget about S for a moment, we just look at this. So he's showing that no matter how large my graph is, right, if I have a valency-free graph, which is arc transitive, okay, then the vertex stabilizer has order at most 48. Okay, and there's been a lot of work trying to see, well, how can we extend that, which motivated the initial Sims conjecture, okay, where if you have a primitive group, can you bound the order of the vertex stabilizer in terms of some function of the size of one of the subdegrees? And that has been, that was proved in the 80s by Prager, Cameron, Saxelin, Seitz. And also there's the Weiss conjecture, which again is, instead of having valency-free, you just have an arbitrary valency graph. Okay, but you look at the local action, and if that local action is primitive, then can you bound the order of the vertex stabilizer? So the Weiss conjecture says that you can, and there's a large amount of work in that. But I don't want to go in that direction today. Okay, but I think Luke Morgan spoke about that here at the program in February. And instead, I want to look more about this bounding S, okay, in the other direction. Okay, when can you bound S? When can you bound S? Can you classify S-arc transitive graphs and or other symmetry-related symmetry conditions? So first of all, I should give a lemma. Okay. And so if I have a graph gamma, gamma is 2-arc transitive. If and only if it is vertex transitive. And if I fix a vertex, so GV, and I look at the action on the set of neighbors, okay, if this is 2 transitive. So my vertex stabilizer is acting 2 transitively on the set of neighbors. So this means that if I'm looking at 2-arc transitive graphs, I suppose I should say if I have an S-arc transitive graph, it will also be S take 1-arc transitive, S take 2-arc transitive. So if I'm looking at graphs which are S-arc transitive for large values of S, then they will be 2-arc transitive. And so the local action is a 2 transitive permutation group. Now, okay, thanks to the classification, we know all the 2 transitive, finite 2 transitive permutation groups. So we have a lot of information here about what the local action should actually be. So that then enabled Richard Weiss, 81. And that is to show that if gamma has valency k at least 3 and is S-arc transitive for some S at least 1, then S is at most 7. So this is as good as we can do. We actually gave much more information than that. Okay, so moreover, that the pair, if I take my stabilizer of a vertex, have a stabilizer of an edge, okay. I should have said if. So if S is at least 4, okay, then the pair GVGE is from one of the examples 1 to 3 there. Okay. Perhaps I should say a little bit about what I mean by G. Okay, so I've given you the full automorphism groups of those graphs. In many cases, you can go slightly smaller and still retain that 7-arc transitivity, 4-arc transitivity, or 5-arc transitivity. Okay, and when I say GV, G given from these examples, either it's for the full group or just some smaller group which retains the transitivity things. Okay. So, but in particular, what do we have? Your valency must be q plus 1, the q is a prime power. Okay. If I look at my local action, essentially it's just PSL 2q, somewhere between PSL 2q and P gamma L 2q. So that's what the local action must look like. And also one thing we should note, which I'll want to use later, is that the edge stabilizers are solid. Okay, so what's this saying? So I'm not saying that the graphs have to come from these graphs, okay, but my vertex stabilizer, edge stabilizer pairs, they do have to come from these graphs. But we also know if I have to be 7-arc transitive, my valency is a power of 3 plus 1. Okay, if I'm 5-arc transitive but not 6-arc transitive, I have to be a power of 2 plus 1 is my valency. Now, you then may ask, well, are these the only examples though? So I want to mention coset graphs. How would I construct a graph in general? Right? I think I would very, very rarely draw a graph. I just construct it from a group. Okay, so if I start with a group G, let's take a subgroup H. Let's take an element little g, which is in G but not in the normalizer of H. And we want such that G squared does land in H. Then we can construct a coset graph. So we can have gamma. This will be the coset graph, which we denote by G, H, H, GH. And we'll have vertices the cosets of H in G. And adjacency so 2 cosets will be adjacent if and only if x, y inverse is in this double coset that I'll specify. Now, if I construct a graph in this manner, well then my group G naturally acts on this set by right multiplication. And it will also preserve adjacency. So I'll get that my group G is inside ort gamma. Perhaps, well, maybe the action is not faithful, okay, because maybe the action on the coset is not faithful, but let's make it faithful. So let's say that H is core free, which means it doesn't contain a normal subgroup of G. Then my action is faithful. And this will be actually arc transitive. Okay. And even better, any arc transitive graph can be constructed in this way. You just take your group G, you let H be the vertex stabilizer, and you take your element little g just to be something which is swapping the two vertices of an edge. Okay. And then your original graph will be isomorphic to the coset graph you get using that GH and little g. Perhaps we should note that gamma is connected if and only if G is generated by H and little g. And we'll say the edge stabilizer is so H is a vertex stabilizer, and an edge stabilizer will be H intersect H to the G. That's the stabilizer of an edge. So if I want to construct graphs with nice symmetry properties, then I can look at just the coset graphs for groups using the properties that I need. Okay. So then using that, I can have a result of Conda and Walker. So this is 98. And that is all but finitely many n an acts 7 arc transitively on a graph, on some graph. Okay. So essentially what you need to do is, inside your copy of AN, you need to find a subgroup which is going to be GV, which is a stabilizer of a point here. Okay, and you're also going to need to find a subgroup GE, which is a stabilizer of an edge here. You want those two subgroups GV and GE to generate all of G, and you'll be able to construct a coset graph in this fashion. Okay? So by looking at the nice subgroup structure, well, by looking at finding your vertex edge stabilizer pairs inside AN, you're able to construct a graph that you're looking for. So they all locally look like this generalized hexagon example, but they're far from being generalized hexagons. Okay. So, what? Sorry, for? Here, this is for all. I've done this for all. Oh, right. I thought they did it for all. Well, actually, yes, I suppose, because this statement here is not really telling you the valency, is it? I think they had, but I would have to look that up and check. Yes. Yes. Yeah, I'm not sure actually what. I'll have to look that up. Okay, so let's say, well, how could we go about trying to look at these graphs? Okay, so let's have some sort of reduction. So a permutation group is primitive if it preserves no non-trivial partition. Okay, so your permutation group always preserves a partition of your set into singletons. It always preserves the partition with just one block. And if they're the only partitions they preserve, they're the trivial partitions, then it's called primitive. Now, suppose that it's imprimitive, so there is some partition. Okay. And if I look at the graph case, okay, so I've got, let's suppose I have a group G inside the automorphism group of my graph. Okay, and let's suppose I have a partition B of my vertex set preserved by G. Then I can look at the quotient graph. So this is gamma B. And what are the vertices? Well, they'll be the parts of my partition. And adjacency, well, if I have two parts of my partition, if in my original graph I can find a vertex V in my first part and a vertex W in my second part, which are adjacent, then I'll say that my two blocks will be adjacent in my quotient graph. Okay, so this is my quotient graph. Now, in general, if I'm looking at two-arc transitive graphs, I could, and if my group is imprimitive, I could take a quotient graph in this fashion, but it turns out you lose too much information in this case. But if we take nice partitions, okay, then instead, if you take, if I have a normal subgroup N of my group G, with at least 3 orbits on vertices. Okay, then you take your partition B to be the set of N orbits. Okay, then this is a partition preserved by G. And then you can look at the normal quotient graph. Gamma N. So instead of looking at any partition and quotienting by them, if we just restrict ourselves to partitioning by orbits of normal subgroups, okay, then this actually is a very useful thing to do. We get two things, and that is that my new graph, so if gamma, if it's GS arc transitive, then that implies that my quotient graph G mod N turns out to act faithfully on the quotient graph, and it is still S arc transitive. And also gamma is the cover of gamma N. So by a cover, I just mean that if whenever I had one adjacency in my block, I've got a perfect matching between. And so then, essentially, if we use this reduction program of Cheryl's, then there's sort of like two base cases that you would need to look at. Right? So there's like two base cases. Okay. And the first is where all normal subgroups are transitive. Now this is where your group is called quasi-primitive. So in a primitive group, all your normal subgroups have to be transitive because your normal subgroups will give you a G-invariant partition. But not every quasi-primitive group is primitive. Then you just take a simple group acting on the cosets of any subgroup. There are no proper normal subgroups. So all the proper normal subgroups are transitive. And then you have another case is where potentially you've got some orbits of size 2. Okay, so then all normal subgroups have at most 2 orbits. And there exists one with 2 orbits. Now in this case, this pops up in your bipartite graph case. Right? If I have a bipartite graph, which means that I've got 2 parts, all edges just go between parts. If I take the index 2 subgroup, which fixes each of the 2 parts, that index 2 subgroup is normal and it's got 2 orbits. And so we land in these cases. Now, okay, so but if we look at these 2 basic cases, again, if I look at the quasi-primitive case, it's probably still too really infeasible. If you were trying to classify all the 7-arc transitive graphs where your group is quasi-primitive, that would be very probably impossible to do, right? If you look at these examples here, AN, right? AN's a simple group, so its action is quasi-primitive. Okay, and so really you're trying to find how can you generate any simple group with some pair of subgroups GV and GE where you know the pairs, right? That would be very hard and too wild to attempt to do. Okay? So but this does give you, though, a nice way of studying them and trying to prove theorems about how the graphs exist. But where we can classify things is Lee in 2001. He classified all 4-arc transitive vertex primitive graphs. Because now you've got this restriction that your vertex stabilizer has to be maximal, right? A permutation group is primitive precisely when your vertex stabilizer is maximal. So now you want to find the groups. Well, you can do some work using the reduction of shell. You can show to be 4-arc transitive, you must be having an almost simple group of automorphisms. Then you need the almost simple groups, which have a maximal subgroup GV given in our known list. Okay. Then you have to see if you also have a suitable GE, which generates the whole group. And by doing that, you can classify the vertex primitive ones. And I won't say what they are, but there's 3 infinite families and 5 individual ones. Okay. And in the sporadic ones, there is a 14 valent one with the monster as its automorphism group. Okay. So there your vertex stabilizer is the same as the vertex stabilizer in the projective plane of order 13. So that's the primitive case, and but I suppose those nice 3 examples I gave you, none of them are primitive because they're all bipartite graphs, because I naturally built them up as a delta 1 and a delta 2. Okay? So they're far from being primitive, okay? But instead they're what are called biprimitive, and he also classified all 4 arc transitive biprimitive graphs. And so what do I mean by biprimitive? Okay, this means that they're bipartite. And there's this index to subgroup G+. Okay, that's the group which fixes the 2 parts of a bipartition, so it fixes these 2 sets. Right? And this is primitive on each bipartite half. And in this case, we'll get 4 infinite families, 3 of which are the ones I gave you. The 4th is just to do with PSL2Q. And 2 sporadics, 1 to do with A6 and 1 to do with M12. Okay. So that's where we can get to for there. Right? If you want to go to 3-arc transitive, I would say that's probably just even vertex primitive 3-arc transitive would be too infeasible because we don't even know what are the possible vertex stabilizers. Right? That's too much hard to do. Okay. So then, okay, I want to take a little slight variation then. Okay, let's look at edge primitive graphs. Okay, instead of being vertex primitive. Okay, and so the study of these go back to, again, well, Richard Weiss in 73. And there are only 4 edge primitive graphs of valency 3. Okay, you get K33. You get what's called the Hayward graph. Which is just the valency 3 graph I'm getting from a projective plane of order 2. And you're getting, there's a Biggs Smith graph on 102 vertices. Okay, and you also get the TUT Coxeter graph, which is just the valency 3 graph I'm getting from that projective, from the generalized quadrangle for SP4Q. So whereas there's several infinite families of vertex primitive valency 3 graphs, you've only got 4 edge primitive ones, so it's quite restrictive. Okay, so then myself and Chai-Heng Lee in 2010. Well, actually, we started doing this, I'm pretty sure we started doing this the first week of my first postdoc in 2002, but it took us a long time to actually sort out the details. So we gave a general structure theory for edge primitive graphs. So I don't really want to go into what the details are, but essentially you've got this primitive action on edges. You can study what types of primitive actions they are. Okay, you've got your own n's got types. You can then look to see what are the possible actions on vertices. Okay, maybe it's primitive. We showed that either it was vertex primitive, or it was vertex bi-primitive, or it was something else which we called a spread of a graph. Okay, and so you can study, that gives you some general way of studying what these edge primitive graphs look like. Okay. People then subsequently use that to classify the valency 4 ones and the valency 5 ones. But we can combine the two ideas, okay, and Li and Zhang in 2011. Okay. Before I say that though, perhaps I should look at what your subgroup structure needs to look like. Okay. So if I'm an edge primitive graph, I've got my group G. I've got my edge stabilizer. This needs to be a maximal subgroup. I've got my edge E. It's made up of 2 vertices. The arc stabilizer is going to be an index 2 subgroup. That's going to be contained in my vertex stabilizer, GV. So to get one of these graphs, I need to have a maximal subgroup with an index 2 subgroup, which is contained in a different maximal subgroup. Okay? And I don't want this one to be conjugate to this one, because that's not going to give me a nice, it'll give me some degenerate graph. Okay? So I've got this configuration of maximal subgroups which I need to be looking for. And then Li Zhang in 2011. Okay, so they gave a complete list of the soluble maximal subgroups of almost simple groups. Okay, so I mean the maximal subgroups which are also soluble. Okay. And then from the original result of Weiss, if I'm 4-arc transitive, then my edge stabilizer needs to be a soluble group. Okay, so therefore I must be coming in from this classification. Okay, and so then they're able to classify the 4-arc transitive edge primitive graphs. And what do they get? Well, actually, they're very good, right? We get the 3 infinite families. So the original 3 infinite families, they're all edge primitive and 4-arc transitive. Plus only 4 others. Okay, you'll get one for you get the big Smith graph again, which has PSL 217. Didn't write that down. No, it's 217, I think. It's either 217 or 213. And then you get one for the Ruud-Wallis group, one for M12.2, and one for J3.2. This is valency 3, it's valency 6, valency 4, and valency 5. So that's all you get. Okay. So really, those nice 3 projective plane GQ generalized hexagon examples you get, that's essentially all you're getting if you're throwing in edge primitivity, plus a few others. Right. Now, in this case, can we go down? Right? I said that for the vertex primitive, it would be too impossible to go down to 3-arc transitive. But actually here we have, we're in a much better shape. So there is a result of a recent result, Blue 2020. And this is if I'm 3 arc transitive and edge primitive. Again, this gets you that G is an almost simple group. Okay, so I just mean abstractly as an almost simple group. And if GV is faithful on the set of neighbors, then your socle of GV must be A7, and your edge stabilizer must be either M10, PGL29, or ORT A6, right, which are all the overgroups of A6 other than S6. Okay. So now if I want to classify all my 3-arc transitive edge primitive graphs, okay, then, okay, in the faithful case, my GE must be one of those. Right, so I look to see which almost simple groups will have one of these as a maximal subgroup, then look to see if I can get a GV being in A7. Okay. And in those cases, I will get 3-arc transitive graphs. And then for the unfaithful case, well, straight away, this knocks out for your almost simple groups. If you look at the classical groups and Ashbacher's theorem, one of your big classes is the C9 subgroups. Okay, your C9 subgroups are almost simple groups. They're going to have to act faithfully on the neighbors because there's not much of a kernel that can be. And so your only C9 subgroups you get would be one of these ones. Okay, and so then that makes this feasible. Right, to go through, you want an almost simple group G, G being a non-C9 sub, well, if it's a C9 subgroup, it's one of these, so you can do it, potentially. Then you find when there's an index 2 subgroup and when you have an overgroup. And so this is what Carlisle King and myself have recently done. But not quite. This is with socle of G, either classical, sporadic, or alternating. So I suppose one thing holding us back for the exceptional group case is that still, when is A6 or a group with socle A6 a maximal subgroup in an exceptional group, that's still open, and so even the faithful case there would be, at the moment, a bit beyond reach. Okay. I wanted to say a little bit about what we got, though. But I've only got 5 minutes. I was going to talk about digraphs as well, but perhaps I'll skip the digraphs and I'll say just a little bit about some of the examples we got here. So we get, we'll get all these examples of course. Okay. We then get some extra ones though. If I just take the n take 1 on 2 and the n take 1 on 2, sorry, the n plus 1 on 2 dimensional subspaces of a vector space over G of Q. And if I take containment as my adjacency, then I'll get a graph. So when n is 3, I'm getting my projective plane examples. Okay, but the larger n, I still get 3-arc transitive. You also get some nice, I suppose, configurations, things like PSL 6 plus or minus Q, extended by a graph, That will have PGL29 as a maximal subgroup, which will have A6 inside it, which is contained in a A7, so that can be my GV. And so in this case, actually, you're inside the SOCL, so it'll be bipartite. And also we get various infinite families like this in PSL and PSU 6Q. And also we get this strange one. Extended by a graph and a diagonal. You go alt A6. This is GE. S6. S7. That's my GV. But here actually this subgroup's far from maximal. It's actually contained in two different groups. This is like in an M22.2 and a PSP 47.2. So this comes up in the spread case. As I said, this is neither vertex primitive or biprimitive. It's what we're calling a spread. Okay? And then we get various others. So we get, essentially we're getting 10 infinite families and a few other sporadic ones. Okay. So in that case, it's feasible. I had wanted to say a little bit about digraphs, but I don't really have much time. But instead, perhaps I'll just say what the main problem is. And that is that, okay, for graphs, you can only be at most 7-arc transitive, and that's it. Okay. For digraphs, you can be S-arc transitive, but not S plus 1-arc transitive for any S. There's a very easy construction. You just take lots of blocks of size k, size k. Now every vertex here is adjacent as a directed edge to every vertex here. You go around the cycle, and so on. That will be S plus 1-arc transitive, but not, sorry, that'll be S-arc transitive, but not S plus 1-arc transitive. Okay? So Prager did these in the 90s. But these graphs are far from imprimitive. Okay? And so she asked, is there a primitive example? Okay? Can you find a vertex primitive 2-arc transitive digraph? Okay? And only recently we've been able to find such examples, but they're only 2-arc transitive. And so really it's still very much open. If I have a vertex primitive digraph, what's the largest value of S you can have? Okay? Here, in some sense, things aren't as nice because you no longer have that the local action must be 2 transitive. Okay? But things are still nice because your vertex stabilizer has a factorization. These two subgroups are conjugate in G, and so are isomorphic, but they're not conjugate in GV. So again, we convert the problem to a question more about factorizations of vertex stabilizers, and again, that enables us, with knowledge about maximal subgroups, to now construct some examples, but we're far from really knowing what the truth should be for values of S. I think that's a good place to stop. Thank you. Yep. 2 at the moment. So we've got one infinite family for PSL3 p squared, and we have another infinite family where we have a diagonal type group. But we can classify all the diagonal type groups. And yes, I didn't say, but we have a reduction. Bing, Zhou, Shao, and I have a reduction that if you can bound S, the correct value of S will come from what you get in the almost simple case. So it is, again, then a question about what can you do for almost simple groups.